Okay, we'll get started in just a moment. Get set up here. Just be a few seconds. I want to try to get everything set up. Moving some stuff around. Hope you're doing well. Let's see. Hopefully you can see my screen. Hopefully you can hear me. Hopefully. Oh my goodness, it's cold in this room. I must be like right underneath the air conditioner. It's freezing in here. I guess it'll keep me sharp though. Maybe wait one more minute. Okay, yeah, so we'll get started in just a second. I don't think I had any, I don't remember. I don't think I had any homework questions over the weekend from you guys. So yeah, if you're getting stuck or anything, or maybe I just don't remember. But if you're getting stuck on anything, just send me a message, send me an email. Maybe it would help if I showed my email. It's freezing in this room. I think we're right underneath there. But as I say, if you get stuck on, I don't think I got any emails from this class. I got from my other class. Yeah. So if you get stuck on a problem or something, it's better to email me at least a couple days before it's due. If you email me, 9 or 10 o'clock tonight, I might get back to you. But yeah, so I see you guys are working on it, continue to work on it. It's due tonight. But yeah, in the future, as we go, if you get stuck on them, just send me an email. Email is the best way. Actually, the best way to get help is to, you can click on that link and it says ask my instructor. So if you get stuck on a problem, that would be my preferred way. It's working this semester and it sends me a direct link to your version of the problem. So that's really helpful because I can see exactly what you're looking at and how I can help you. Okay. So continue to do that. And as always, we have 0 extra time in class today. I'm going to be teaching as fast as I can speak. I have so much to go over, as always. So if I goof up or something, don't hesitate to stop me. But yeah, again, I'll be going kind of quick because I have to get 2 weeks worth of material done and basically an hour, about 2.5 hours. So I gotta do it quick, right? But this is being recorded and I'll post that video tonight. And hopefully you saw the video that I posted last week. And I chopped it up so you can go straight to the problem. Maybe we'll talk about that after the break. I'm just going to dive right into some problems and just kind of get into it. Yeah, so this is section 2A. We got 2A and 2B to get through. And this is all about derivatives. And we talked about derivative last week, but we never really called it that per se. So what we said was we had the difference quotient, and that was that x plus h minus f of x over h thing that we did. We also talked about slope of a line. We talked about that a lot. And this is going to kind of connect those ideas. So, and we also obviously talked a lot about a limit. That was mostly what we focused on, was limits. So in this one, we're going to introduce the derivative. And so this is one of the core things that you learn about in calculus. So I would say the first cornerstone is the limit, and everything else is sort of defined by the definition of a limit. So once you go from limits, then you're going to go to derivatives and so on and so on and so on. We're going to get, later in the semester, we'll get into antiderivatives, which is also extremely important. But in this one, we're introducing, and I would say diving pretty deep into derivatives today. Okay, and there's a lot of different types of derivatives, and there's a lot of tricks that I need to show you. And so I'll try to go over as much as I can. All right, so the beginning here, this problem that should be projected to you out in cyberspace there. So hopefully you can see it. Should have pulled up the chat. So talk to me question. Yeah, please do. Chat, hopefully. Got the chat, I don't catch that any questions. Okay. So let's look at this one. So we see f prime of x, that's going to be the derivative. The derivative of the function equals the limit as h approaches 0, f of x plus h minus f of x over h. Okay, so that's exactly what we were talking about last time. And then we're going to find that at the value of x equals 7. Okay, so how can I determine this? Well, we did the difference quotient before. That's what we learned about before. This is the function that they're giving me. So let's try to find the difference quotient of that, and then we're going to take the limit as h approaches 0. Okay, so it's going to be the limit as h approaches 0 of f of x plus h, which would be 6x plus h squared minus 6x squared over h. I think I plugged that in correctly. Now I want to expand and see what I can drop off, maybe reduce. So that would be 6x squared plus 2hx plus h squared minus 6x squared all over h. Okay. And now I want to distribute the 6. And I don't think I have enough space to do it there. So this would be the limit as h approaches 0 of 6x squared plus 12hx plus 6h squared minus 6x squared over h. And you're going to know you did this right if the h on the bottom can be reduced away. That's exactly what we need to happen. We need to cancel out that h in the bottom. We want to cancel the bottom h. We really need to do that. Okay, what can I reduce? Looks like I can reduce 6x squared. Those cancel. They're equal and opposite sides. And from there, we have the limit as h approaches 0 of 12hx plus 6h squared over h. And what happens is everything has an h attached to it, so we can reduce that. The limit as h approaches 0, take an h out, you get 12x plus 6h over h, and as promised, that h reduces away. We're almost done with the problem. The limit as h approaches 0 of 12x plus 6h. Now let's let h go to 0. If h goes to 0, what happens? Well, then it's just 12x, right? Then it just becomes 12x. So I think that f prime of x equals 12x. Okay, and then it says if this version of the problem says evaluate that when x equals 7. Okay, so f prime of 7 equals 12 times 7, and that's 70 plus 14, and that's 84. So I think the answer is 84. That's the idea. We're going to see today that that is correct. There's nothing wrong with that. That's by definition what's going on, but we're going to see that there's a few tricks of the trade for things like this. Okay? So even though that's true, and that's by definition the truth, well, it turns out that all of these are kind of the same, especially if they're just a polynomial like 6x squared. Since all of these have the same version, we can notice a few things about what's going on, and then we can come up with a few rules to speed things up and make our lives a little bit easier. Okay, but by definition, that is derivative evaluated at x equals 7. And I remember when I took calculus, we always had to, take the derivative by the definition of a derivative, evaluate it here. That's exactly what this problem is. So back when everything was paper and everybody was in person, that's what you would do. You would take the derivative by definition. That's what we did. We evaluated this x equals 7, okay? All right, let's keep going. We'll see what's going on. Maybe I'll even just point it out now. What really happened to this? What really happened is that we noticed that f prime of x equals 6 times 2x. That's what we found. 6 times 2 is 12. We found that that equals 12x. Is that always going to be the case? Yeah, that's what ends up happening. So what's going on is that we've showed, one example is not a mathematical proof by any means, but what's happening is with this 6x squared, this 2 is coming down. And what we're doing is we're going to have 6x, let's write it like this, 6 times 2x, and then it's 1 less than it was. 1 less, so it was 2 minus 1, that just becomes a 1. So we just have 12x. And so that would be true with any of the numbers. All right, so that's going to be called the power rule, which we're going to build up through this homework. That's what's going to happen. That's what we'll see. Okay, and the next one that says graph the function f of x equals 2x squared minus 5x plus 3. Okay, well, graph the function. We've been graphing, parabolas since high school. That's not too much work there. Of course, you can just use a graphing calculator for your homework as well. That's no problem. Or your quizzes. That's not really a big deal. But what is new is the tangent line, and find f prime of x by determining the limit as h approaches 0. So that's something that we have most likely have not been. So how do we do that? How do you find the tangent line when x is 0, and how do you find the f prime of x by the limit as h approaches 0? So let's try to find it. Okay, so I don't have a ton of space in this problem. Let's see if I can find some blank space. No? Okay, I'll just do it up here. So the limit as h approaches 0 of f of x plus h is 2x plus h squared minus 5x plus h plus 3 minus the original function 2x squared minus 5x plus 3. Okay, and that's all over h. So what I need to do is I need to expand those terms with the x plus h and then reduce anything that I possibly can. So that's what I want to do next. So the limit as h approaches 0 of 2 times x squared plus 2hx plus h squared minus 5x minus 5h plus 3 minus 2x squared minus plus 5x minus 3 over h. So far, it's just a lot of algebra. That's just what we're doing now. It's just a lot of algebra. This was supposed to be a 3. All right. Let's see what happens. So from there, I have the limit as h approaches 0 2x squared plus 4hx plus 2h squared minus 5x minus 5h plus 3. Let's see. I think that was supposed to be a minus sign. Minus 2x squared plus 5x minus 3. Yeah. Minus 5x minus 5h plus 3 minus 2x squared plus 5x minus 3. This is the part where we reduce where we can, and we should be able to reduce quite a bit. The 2x squareds go away. The 5x's go away. The 3's go away, right? What I seem to notice is that everything that has nothing to do with h goes away, it reduces. So that's interesting to me. Okay, and this is really ugly, but I'm going to stick this over here. All right, so the limit as h approaches 0 of 4hx plus 2h squared minus 5h all over h. Now we want to do the part where we factor out the h. So the limit as h approaches 0 of h 4x plus 2h minus 5 over h. Get to finally cancel that h at the bottom. That was the whole goal, cancel the h in the bottom so we don't divide by 0. As we let h go to 0, what happens? You're going to get 4x minus 5. So that's finding the derivative by definition. That's what we did by the definition. Okay. Well, let's see. Whoops, nope. That's beyond ironic. I said, let's see, and then I close the window down. Okay. Let's go back to the original function and take a look at what's happening. So when I took the derivative by definition, what do I see? I got 4x minus 5. And I said that there was this weird thing with the exponents that goes on. So the exponent comes down, and then it gets subtracted by 1. And notice what's going on here. You have 2x squared minus 5x plus 3. So what I think is happening is that 2 is coming down, 2 times 2, x, and then with the 5x, there is just an exponent of 1. Okay, so that's minus 5. When we subtract 1 from 1, we get 0. So that's an exponent of 0. So it just goes to 1. So now it's just 4x minus 5. And the 3 didn't have an x, it was already 0, so it just drifts away because it was a constant. Okay. So already I can see a pattern, at least when things are just a polynomial. It seems that there's a pattern to what happens when you're taking the derivative. Well, what is the derivative? What is the derivative that we're finding? The derivative is the rate of change of the function at that moment or at that precise location. So I'm going to take a picture of that so we have that for our records. I'm going to close it and I'm going to show you what I think you can take from it. So f prime of x must equal 4x minus 5. Okay, that's the derivative. What does that mean? What does that mean that the derivative is there? Okay, well, you remember when we were talking about lines and we'd have slope? Like the slope of a line is m, and that was the rate of change. It's either going up or it's going down. The derivative is the slope at any point on the function, but now we're talking about curvy things. So we're talking about curvy things. So it has different rates of change. It has different rates of change. Let's look at the graph of the function and maybe I can explain it that way. So hopefully you can see the graph there. You read it. Okay. So notice if I zoomed in really close to this area right here, if I zoomed in right there, that's basically a straight line. If I was just looking at that piece, it's pretty much a straight line. And there must be some slope to that straight line, right? There's some slope to that line at that point. Okay, at that point, there's some slope, right? Some rate of change. But it's different over here. In fact, it looks like it's the opposite. So it's going down on the other side, right? So the slope is changing depending on where you are in the parabola. So depending on where you are, the slope changes. If you give me a precise x that you want me to look at, I can give you the rate of change. And that function is the derivative. That function is the derivative. So f prime of x equals 4x minus 5 is the slope, the rate of change at any given x on this parabola. That's the idea. So that's the idea that we're looking at here. When it says tangent line, that's what it means. It means, okay, if we're looking at right there, what's the slope of the tangent line? It's the line that's just touching the function. Okay, that's the idea there. Okay. So when we're dealing with things that aren't just straight lines, that are curvy like parabolas or cubic functions or that kind of thing, it depends on where you are. The rate of change depends on where you are. So if you're right here, the slope is 0. So if you're down there, the slope is at 0, as opposed to a positive number or a negative number. So right there, it's just 0. It'd just be a horizontal line right there. And there will be questions later where it'll ask us, find the location where the slope of the tangent line is 0. And that's where it's coming either, that'll be its lowest point or its highest point. That's the idea. Okay. So we found the derivative. That was easy enough. And then in some way that was just review from last time, but there's the derivative. Okay, and then it says, draw the tangent line to the graph at the point where x equals 0. So x equals 0. This is where it is. So we know what a parabola looks like, but what is this tangent line as x equals 0. Right there, the origin, that's where x equals 0. Right there is where it's going to intersect the parabola. And if you want, you can even find what the slope of that tangent line is by plugging in x equals 0. So if I plug in f of 0 into the derivative, that's 4 times 0 minus 5, which equals, oh, I wrote negative sign twice, is negative 5. So we see that the slope on the parabola at x equals 0 is negative 5. Okay. That's the idea. So there's the tangent line. Okay. And then find f prime of 0. The slope should match the line that you drew. Yeah, it did. Let's go down. And there it is. So there's our f prime of 0 equals negative 5. That's the slope on the parabola at that point. Okay. So we found that f prime of x equals 4x minus 5. If we plug in 0, we get negative 5. Negative 5. That's the slope of the function at that point. Okay, x equals 5. That's the idea. Later, we'll be asked to find where is this located. Okay, so they'll give us some rate of change and we have to find it on the function. But here it's straightforward. You can just find it. Right. This one is similar, but the reason why I want to show it is because the variable is in the denominator and that can be more complicated. All right, so I'm kind of leaning towards just going straight for the power rule, but if you'd like, I can show you by definition as well. That's what the question technically asks, is to do it by definition. Maybe I'll just do both. Get your money's worth. So I'll show you how to do it by definition, and then I'll show you how to do it by the power rule. Okay, so let's do it by definition. Well, for this function, the limit as h approaches 0 of f of x is going to be, and this is 8 over, this is so small, I can't even read it. Let's go over here. I'll switch colors too. Okay, this is the limit as h approaches 0, 8 over x plus h minus 8 over x all over h. Okay. That's by definition us plugging in it. Now we just have to play with the algebra of it all. Find this. H approaches 0. And so I'm going to kind of mess around with these fractions here. So I'm going to put that h in the bottom. I'm going to put that to the side for myself just for a second. And what do I have? I have 8 over x plus h minus 8 over x. Okay. Now I think I'm just going to cross multiply. I think that would be the thing to do. So we have that 1 over h. Eventually, I want to try to get rid of that. That would be my goal. 8x minus 8x plus h all over x plus h. And I think I need to expand now. 1 over h. So the 8x minus 8x is going to cancel. 8x minus 8x cancels. So we're just going to be left with negative h on top. Negative h. And we still have the x. And if we like, we could do x squared plus hx. Okay. Now I can cancel that h in the denominator, which is good because now I'm not going to divide by 0 as it approaches. Almost there. The limit as h approaches 0 of -1 over x squared plus hx. Now, as I let h go to 0, what happens? I'm just going to be left with, I feel like I dropped off an 8 somewhere. What did I do? Oh, my apologies. I dropped, it's like, that's not right. Sorry. That was 8h. Sorry about that. Now, there we go. That looks better. Dropped an 8 there. Picked it. Oh, color. Sorry. There we go. That's better. Now, as I let h go to 0, that's only going to be this part. That's going to go to 0. And I'm just going to be left with -8 over x squared. So by definition, that's what I think the derivative is. So let me write that down. F prime of x equals -8 over x squared. That's what I think. By definition, that's how I think we would find it. Let me save a picture of that. Okay. Now, is there any way to find that with just the exponents? We were talking about that earlier, where we noticed that there was something going on with the exponents. Is there a way to find that just using the exponents? So what is the exponent of x here? F of x equals 8 times x to some exponent. What is the exponent when the variable is in the denominator? Does anyone know that? What's the exponent for x when it's in the denominator? Does anyone know? You need this one.
Negative.
Yeah, exactly right. It's a -1. Okay. So that's like 8 times x to the -1. So if this rule works out like I think it does, then f prime of x equals 8. That -1 is going to come down. Okay. We'll still have x, and then it'll be -1 minus 1. It's still going to decrease by 1. Okay, so the previous exponent comes down, and then whatever it was is going to be decreased by 1. So then I think this will equal -8 x to the -2. So if I rearrange that, if I go where I only have positive exponents, then this would be -8 over x squared. And that's what we found by definition. Okay. So it looks like if you can rewrite things as an exponent, then you could get the derivative really quickly. Okay, we still have the definition of a limit in case we need to go back. We still have it. But if it's if we can write it in terms of an exponent, looks like maybe we can do it in this way. And that might save us a lot of time and energy to do that. And in fact, I think it will. Okay. All right, so that's what I think the derivative of this function is. It says draw the tangent line whose coordinates are, x coordinates are 0 and 2. Okay, and then find f prime of 0, f prime of 2. Well, since I'm dealing with those right now, let me just go ahead and plug those in. So f prime of 0 is -8 over 0 squared. Uh-oh. I'm dividing by 0. That's not good. So I don't think that exists. I think that's undefined. Undefined. What about f prime of 2? What is the slope of the function the rate of change of the function at x equals 2. Looks like it's -2 if I did that right, because that would be -8 over 4, and that would just be -2. So that would be the rate of change of the function at that moment. Okay, so we know that this function looks something like 1 over x, right? Which has those asymptotes. It can't actually touch 0. Okay, of course, you can graph this in your calculator, but you know that it's going to look something like 1 over x. This has times 8, so it has that transformation. But this is what I think the graph is. And we can see what happens when x equals 0. Well, just like 1 over x, you have this asymptote, and you have that even if you multiply that by 8. But what is the rate of change when x equals 0? Well, it's not even, we can't even see it on the graph. Okay, so it's certainly undefined. It's undefined for sure. Okay, so that makes sense. And then what is the rate of change when x equals 2? Well, that's 1, 2. So that would be right there. What is that rate of change? We can see that it is going that way. It is negative. And we found that the rate of change there is -2. It's going down. But it will change as it goes. That's going to have a different rate of change over here, which will be a little different over here. So that's the idea. Okay. So again, the derivative of the function is the rate of change at whatever point you want to analyze it. And we found tangent line at that point, x equals 2 would be right there. That's the line that just touches it. That has that slope and that x coordinate. Later on, we'll talk about how to find that one. Right now, we're just identifying. Again, when you're doing your homework, I might suggest you can always use Desmos to graph these things. I think that's pretty helpful. I prefer it myself. I think it's a good program and it's free and you don't even have to sign anything up. Okay. Select a choice. We found that it's undefined when x equals 0. There is no rate of change that doesn't even exist. So I put no solution for that. And then f prime of 2 I found was -2. So hopefully it's clear. Similar, this is a similar idea. This is number 5, but with this, they just want us to jump right in and they say, okay, find the tangent line. They give me the function, they say, find the tangent line. Before I just had to identify what the tangent line would look like, but now I have to find it. All right, so how do you find the tangent line? Well, what did we do before? We found the derivative of the function. Then we found what the rate of change of the function is at that point. And then somehow we have to find a line after we do that. Okay, but we remember how to find a line because we practiced that last week and we all took algebra class. So we just need to remember how to do that, but we know how to do that. Okay, so this is very similar to that 8 over x I had before, but now it is 2 over x. Okay, but it's the same idea. And if it's okay with you, I'm just going to do the power rule. I'm not going to use the definition of limit, but we just saw how that worked. Okay. And in fact, we kind of already know what this derivative is. Instead of an 8, it's just a 2. But I'll go ahead and spell it out a little bit more than that. So this is 2 x to the negative first. So if we want to find the derivative of this function, I think you can bring down that -1. So that'd be 2 times -1 times x, and then it would be -1 minus 1. We're going to decrease it by 1. That seems to be the pattern. And so that's negative 2x to the negative 2. So I think derivative of the function is negative 2 over x squared. And that's what we found before, except it was the number 8. And if you have the number 7 or whatever, that's what it would be. Okay. So there's the derivative, but that's not what the question asked. The question asked was for the tangent line. Okay, we have to find the tangent line. Well, I found the derivative. Now I need to find the rate of change at the point of interest. What is the point of interest? They want it where x equals 7. Okay. So that implies that the derivative at x equals 7 is negative 2 over 7 squared, which is negative 2 over 49. Right there, I mean, you can see what my answer is, so you can start putting the pieces together yourself. But that is the rate of change of the function at this point, okay? If we start connecting this to real life, not just algebraic functions, this might be how your business is decreasing, or maybe this is how your car is slowing down, or rocket ship is slowing down, or whatever. Okay. But at this moment, that's what the rate of change is. So the rate of change at x equals 7 is negative 249. Okay. They didn't ask for the rate of change. They asked for the tangent line. Okay, but I think that means m equals negative 249. So you remember lines, right? Y equals mx plus b. What we just found was m. We found m. Okay, so we have m, and they gave me a point. They gave me the point 7 2/7, so I can find my y-intercept. Okay, so that means we have 2/7 equals negative 249 for the slope, 7 for the x plus b, and I can solve for b. Okay. Let me rephrase. Well, that's what I want to say, but if you have a slope here and you have a point 7 2/7, find the line. That's what we're doing now. Okay. Looks like we can do a little bit of reducing. So we have 49 over 7. So that would just turn into 7. Okay. So we have 2/7, and that equals negative 2/7 plus b. And that would imply that b equals 2/7 plus 2/7, which is 4/7. Okay, I have my slope, I have my y-intercept, I have my line. So that means y equals mx plus b equals y negative 2/49 x minus 2/49. And that was supposed to be a 4 and a 9. Okay. That's the idea. This is a really important calculation for us. Take a picture of it. I mean, the numbers are whatever, but finding the tangent line is one of those core things that you learn in calculus class. So I would just about guarantee it's going to be on your midterm. Any questions about it? Is there anything I can go over again? Does anyone want to see me do the problem again? Is there anything you'd like to see me do again? Do you want to see the problem again? Anything I can talk about again? Well, note takers, I'll just say, what did I do? The first thing I did was I found the derivative. So find the derivative. Second thing I did was I plugged in the x coordinate into the derivative, and I found the slope, the rate of change at that point. Okay. was the second thing I found. The third thing I found was the line. Well, I guess the y-intercept. And then I found the line. So what are the steps? Find the derivative, find your slope, find your y-intercept, and you got your line. That would be step-by-step guide. And that would be true with any function that they might throw at you, or I might throw at you, or that you have to analyze in your own research. Or do this one, and I am going to do that one. And we can talk about both of them because I don't have to do too much for this. Let's just talk about where things, remember we were talking about continuous last time? We talked about when a function was continuous or discontinuous. Now there's this point of contention, which what is continuous and what is differential? And I will fully admit to you, I did not understand this point at all when I was a student. I did not get it. I don't think I got it until much later. A function can have a derivative, and that would imply that it is continuous. It has to be continuous to have a derivative at that point. But what's really weird, and the point I did not understand as a student, or maybe I thought I did, but I don't think I genuinely understood. It can be continuous and not have a derivative at that point. Okay. So now I claim I understand it. Let me see if I can explain it. Okay. Let's look at this point right here. Right there. Okay, you're going up the hill, and then all of a sudden there's like a hole. There's just a hole there. Okay. There isn't any point that's missing on the graph. As you go, you're going up, and then you kind of fall down into the hole right there. And then as soon as you go a little bit more, you're back up here. Okay. So there's nothing missing. There's nothing missing. But it's not differential at that point. Okay. And that has to do with the limits of remember the limit, if the limit exists, then it has to be equal on both sides. Do you remember that from last time? Well, that's true with derivatives too, and these would not be equal at that point to what they were pointing at before. So the derivative doesn't exist at that point, but it is continuous at that point. There's no point in which it doesn't exist, at least right there. So Kelsey, I'm gonna pick on you. I'm gonna randomly pick a student. Does it make sense? It didn't make sense at all when I was in your seat. I didn't get it.
So the limit doesn't exist, but the derivative does?
The derivative doesn't exist, but it is continuous. So what does that mean? It means that there is always something, there's some output value anywhere right there where I circled. All right. If you go really close to that hole, it's there, then you drop down into that hole, okay, and then you pop back out. Right? So there's nothing missing. Even though there's a hole, we kind of patched it up, right? It's a patch job. That's fine. So that we say that's continuous. But there's no derivative at that point. There's no derivative of that. That has to do with the limits that we talked about last time. So it's confusing, okay? So the fact that it has a derivative implies that it's continuous, but the fact that it's continuous does not imply that there's a derivative, all right? And I can prove that point from a graph all the way up to graduate school, okay? It might have been up to that point that I actually understood what this is talking about. Hopefully you understand it right now and you're not as dense as I am. But that's the idea. So even though there's no point in which it doesn't exist, you always have some output value. It doesn't mean you can take the derivative here. So we can't take the, I'm claiming I can't take the derivative. That's the idea. And then the other idea I want to bring up is that corner piece there. There's this point right there where it's kind of folded. It's like we folded a piece of paper. We say you can't take the derivative at that point either, because what's going on is those points get so close together that it becomes where you can't understand what the derivative is. So we say that's not differential at that point. Okay, that's the idea. And where that's really going to come up a lot, and we'll see it in the homework, that comes up a lot when f of x equals the absolute value of x, because the absolute value of x has that corner, has that like corner piece there. We'll get into it when we get into it, but that's the idea. So all you're really asked to do this week is to just pick out those points where it's not differential. And I think that occurs at 1, 3, and 5, right? So let me point those out to you. X equals 1, it's right there. That's that corner piece. I say there's no derivative there. 3, I say, even though it's continuous, still no derivative there. And then here we have that same problem also, where even though it's continuous, there's no derivative. Just kind of loosely, I'm not proving anything, but you guys wouldn't want to see the proof anyway. Okay. All right. All right, that's the idea. And it's fairly, if you can see it, it's fairly easy to apply it. Next one asks a very similar question. Let's talk about it. It says list the points in which it's not differential, where you can't take the derivative. Well, that's where these things come up. Okay, where is it going to come up? Well, we're good at x0, at least on my graph. We're fine there. x1, we have a bit of an asymptote here. So I can see that the limits are not agreeing. One's going to go to infinity, one goes to negative infinity. That's a big problem for us. So I don't even think it's continuous at that point, let alone differential. So x equals 1, I'm going to have to say, no, it's not good for us. Can't take a derivative there. What about x2? x2, it looks like there's a hole, and at least the way it's projected right now, I don't see a patch job. So it's not even continuous. But that does not look like it's going to work out for us. Here, x3, it kind of looks like there's a bit of a corner piece. That could be a problem. And then x4, it looks like we have a discontinuous point here. But I'm kind of concerned about x3 as well. Looks like there's a corner, even though it was patched. Looks like there's a corner. So I'm kind of worried about x1, x2, x3, x4. Right? Those are just visual ideas of these things. And of course, if you go on into math, which each and every one of you can, then you have to prove all these things. But right now we're just looking at graphs, just getting the idea. So even though a function is continuous at a point, it doesn't mean you can take the derivative. I fully didn't understand that as a student, but now I'm trying to show you what that means. Okay, that's maybe the best guess. Maybe that's why I didn't understand it. It's possible I didn't understand it because when I took this class way back when, we did it all through trying to just look at the function. And I think I got kind of lost there. I think visually it makes a little bit more sense.
X2 wouldn't be continuous, because it wouldn't have anything to fall into.
Oh, yeah. X2, did I not circle that?
No, I was just making sure.
Oh, yeah. So that's a problem. It's not even continuous there. So not even continuous, so that's a problem for us. We can't do that one. X1 here doesn't work for me because that's not continuous. They're pointed in the opposite directions. That's not good. X3 is because of that corner. The corner is going to give us too much trouble, so we can't do that. X4, it's not continuous at that point, so it's certainly not differential. X5 looks okay to me. I think that's fine. Looks like it would be okay, at least from graph. Okay. That's the idea. Okay, so that's what I got and why I got it. I don't have this memorized, so I'm trying to remember what. Draw the graph that is continuous but not differential at x equals 4. Here, you just have to kind of pick, right? There's nothing to derive with something like that. We're just picking which one. I claim it's this, which just happens to be what I'm getting to, which is that absolute value of x. The absolute value has this point at which it has this corner where it just all of a sudden switches its rate of change. Okay, that means that the derivatives are not lining up, just like our limits didn't line up last time. And we also talked about that the derivative is really a limit, so that's why it's not working out. But I think we can all agree that at this point it was going this way, it was going down, and then all of a sudden, flick of a switch, it's going the other way. So I claim that it would not have a derivative at that point, even though it is technically continuous. So that worked for mine. What was the next one? Next one is just picking out, again, it's just picking out which one's correct. Which of the lines in the following graph appear to be tangent lines? Why or why not? Remember, tangent lines go along with the line. They just touch the line and they go along. So let me switch to blue. And then this is not a tangent line. So that part is just not a tangent line. It's perpendicular to the line that we see. So that's just not even a tangent line in the first place. Which of the lines following appear to be tangent lines? L2, at least for mine, looks good. It looks like it's following along with the function at that point. L3 looks good to me. It looks like it's following along with the rate of change. L4 seems to be doing the same. L5 does not. L5 seems to be perpendicular to the function at that point, which maybe you would be interested to that with that for some reason, but we're not at this time. And then L6 looks good to me. Looks like it's touching the line and following along with it. Okay, so that's what I think. So I would exclude it. I don't know if you have similar graph to mine, but I would exclude L1 and L5 if you have something similar going on in yours. And then why do the lines selected above appear to be tangent lines, or why the other lines are not tangent lines? The slope of each tangent line is equal to the slope of the graph at the point of intersection between the graph and the respective tangent line. The other lines are not parallel to the graph at the point of tangency. So that's what I'm trying to say here by crossing this out, is I'm saying this is perpendicular. So this is perpendicular. It's not the rate of change at that point. It seems to be perpendicular to that. That's fine. Maybe we would be interested in that for something else, but the tangent line is the one that follows along with it. That's what we were talking about now. So we want the rate of change of the function at that point, and that's also here with L5. Okay. But I'm not sure with your homework if it's the same or different. But that's the idea. Okay. Can't remember what 10 was. All right. I'm going to go over 10 as well. Consider the function g given by g of x is the absolute value of x minus 5 plus 1. What I want to call to your attention is that with the absolute value of x, we have this corner piece. And that's not differential at that point. Okay, so we have a big problem there. So we have to look out for it. Now, everywhere else I claim is differential. I'm not going to prove that. I'm just going to say everywhere else is differential. And it turns out it's just a line everywhere else. Everywhere else it's just a line. So what x values is the function not differential? It's not differential at x equals 5. That's where we're going to see. If you look at this function, g of 5, 5 minus 5 plus 1 is 1. That's fine. That's where it occurs, but it splits, right? So if you graph this, you're going to see that corner piece. You're going to see that it has that corner right there, and that happens at x equals 5, and we can't take the derivative. Why can't you take the derivative? Well, it's not lining up correctly. Right? Remember, the limits have to line up. The derivative is defined as a limit. So that's the issue. Everywhere else is just a straight line. This is a negative line. This is a positive line. So that's not that big a deal. And if you want something like, what is the derivative at x equals 0, you can just find the slope at x equals 0. That's what you have to do. Okay, it's just a straight line. So it's not that big a deal. Maybe I'll just do one of them and then I'll leave the rest for you, because it really is just like looking at two different straight lines. It's not that big an issue. Let's talk about this one. So g prime of 0, what's going on at 0? Well, what is the function? Oops, it's g. G of 0 equals 0 minus 5 plus 1. And that is negative 5 plus 1, that's 6. Okay, so now we have the point 0, 6. Well, I claim it's a line. We really only need derivative, or I'm sorry, we only need the slope at that point. So if we want, I think actually what I did to solve this is I just looked at what happens at g1. And so right there, you can see, okay, it's decreasing by 1. That's all I did. So it was 6 is going to 5. It's just going negative 1. So it looks like the slope is just negative 1. That's how I did it. Whoops, I meant to switch colors. It's just like looking at a straight line. So it's just going down by 1. It's going down each time. And then you might imagine, okay, this is just the reflection. So that's probably just going to be positive 1. Okay. Does that make sense? Any questions about that? The really interesting thing is what happens at that corner piece, and we say it's not differential there because the limits won't line up, and derivative the limit. Any questions, comments, or concerns about that? I think it comes up a few times, but it's pretty easy because it's just 2 lines, and you're just finding the slope of the line at that point. It's not so bad. Okay. I'm trying to remember which ones I need. We need to go over some later ones. Let's talk more about that power rule. So here we want the derivative. Now, I guess we should talk about this notation too. This is called Leibniz notation. Not that you worry about that. It just means find the derivative. For our purposes, this means the exact same thing as f prime of x, which, as we know, means the limit as h approaches 0 of f of x plus h minus f of x over h. We're going to say those are all the same thing, all the same thing. But we've been kind of playing with this exponent thing, exponent game. And what is the exponent of x here? Y equals 4x to the 1, right? So what happens if you just bring the 1 down? We'll say y prime equals 4 times 1 x to the 1 minus 0. I'm sorry, What am I talking about? X minus 1 equals 0. And so the x just goes away. So it just becomes 4. So the rate of change, the way y changes over x changes, dy dx just equals 4. That's the slope of the line. It's just the slope of the line. Dy dx. Now, rise over run. Rise over run, right? All right. You can also see if you just have a number times an x, it's just going to be that number. That's the idea. Let's keep going because we have to go over some other ones. Find a good one. I wouldn't say this is great. I mean, it's fine, but probably have to go a little bit faster. How can we play with the power rule here? So we have 7x to the 7th. If I bring that 7 down, 7 minus 1 turns into a 6, and we have 49x to the 6th. Okay, so easy stuff, I hope. That's just power rule. This is called power rule. Power rule. Just dealing with the power. Okay. What if it was negative? What happens? Okay. 6x to the negative 2. Well, if we bring down that negative 2, 6 times negative 2, x, negative 2 minus 1 turns into negative 3. So we have negative 12x to the negative 3. And you can see the computer accepted that. You could also write that as negative 12 over x to the 3rd. Sometimes we might write it that way too. Either is fine. Okay. That was 17. What's 18? All right, let's look at a full-blown polynomial there. What happens? Now, I claim that if you remember our sum of limits, that you could take the limit individually. If you remember last time when we did that, I mean, I think there was only 1 or 2 homework questions about it. But if you had things being added, that you could take the limit individually, you could break it up. And I claim you can do that with derivatives too, since they're just a limit. So I think, well, I guess what I'm saying is, you know, the limit of the sum is the sum of the limit, and that means the derivative of the sum is the sum of the derivative. Okay. What does that really mean? It means we can just take the derivative piece by piece. So that's what I'm going to do. So I have 4x cubed. So if I bring that 3 down, and then I have x 3 minus 2. Okay. Next piece is minus 10. So that's minus 10 times 2, x 2 minus 1. And then we have 12. So that's 12 times 1, x 1 minus 1. And then we have 5. And that will just get lopped off because that's a constant. Okay, there's no rate of change there. So let's clean this up. 4 times 3 is 12. And that is 1 squared minus 20x plus 12. Okay. X to the 0 is just 1. It's from intro algebra, but we need it. So that's how you can take the derivative of a polynomial without having to do by definition. Because definition, you can imagine, we can do it, but it's going to take us forever. And since these things have a pattern, we might as well use the pattern. Right? So you're just bringing the exponent down and subtracting by 1. If it was already 0, like dy of dx of just 5 just equals 0. There's no rate of change for a constant. That's the idea. Keep going because we got harder problems coming. Let's see what 20 brings. It's interesting. So what would dy dx of this equal? If we bring down 0.25, x 0.25 minus 1. Okay, I have 25 cents. Take away $1. You get negative 75 cents. 0.25 x to the negative 0.75, and then you could write that as 0.25 x 0.75 if you like. So that's if you have fractional exponents. But that's probably shouldn't bring it up because I don't have any time, but I mean that's also true. That means the same thing. Like x to the 0.25 is the same thing as x to the 4. It's still the same thing. But we don't have to deal with it. Any questions about the power rule? Does it seem easy in the chat? Can you get a thumbs up or thumbs down? If it seems okay, bringing down the exponent. We're going to do it a lot. Seem okay, chat? Thank you. Okay, this is more with fractions. So we have y equals, I'm just going to write it a little bit different. We have x to the first there. And if I bring down the 1, dy dx would be 7/4 times 1, x to the 1 minus 1 is just 0. So you just get that constant that was in front of it. So you just get 7/4. Nothing too wild yet. Seven. Right. 27 is 2. I claim that we can take the derivative of each one separately, put them together, and that's the same thing. Since we could do that with limits, I claim we can do that with derivatives. So let's see what it would be. If I rewrite this as y equals 1/10 x minus 10 x to the negative first, we can start using that power rule. So what happens? Dy dx, bring down the 1, nothing happens. X, 1 minus 1, x is just going to go away. What happens over here? Negative 10, 1, x to the negative 1 minus 1. Right? So what does that mean? Well, it means you have 1/10 plus, because we have minus times minus, so that becomes plus 10 x to the negative 2. All right, so that means we have 1/10 plus 10 over x squared. Just bringing down that x squared. But I'm really thinking of them as separate. If they're split up by addition, I claim that I can just take them separately. So think of them all the same. Say, picture that one. What's 29 bring us? If f of x equals this, find f prime of 1. That means find the derivative of the function and evaluate it at x equals 1. Okay, so what is f prime of x, which is that dy dx, or we could do it by definition, but I don't want to since I don't have to. We have 3 times 2 x 2 minus 1 minus 2 times 1 x 1 minus 1, and the 5 just goes away. It's already 0, it goes away, constant goes away. So we get 6x minus 2. Now we're supposed to evaluate x equals 1. So f prime of 1 equals 6 times 1 minus 2. That just equals the number. So that would be the slope of the function at x equals 4, the rate of change. That's the idea. I keep going kind of fast because I think I could have sworn there was some tricky ones, really tricky ones down here. Find the equation of the tangent line of the curve at 0.20. This is a good problem, but it's not the one I'm looking for. 46. I already clicked it, so let's do it. Okay, find the equation of the tangent. Remember, a line is y equals mx plus b. So let's do it. Number 31, we have f prime of x to equal 3x squared minus 4. Here's my derivative. They want it at the 0.20. So if I plug in 2, I get 3 times 2 squared minus 4. 12 minus 4 is 8. So that's what I think the slope is, that point. Y equals mx plus b. I know what my y is, I know what my x is, I know what my slope is. 0 equals 8, 2 plus b. So I just subtract 16 from both sides. B equals negative 16. B equals negative 16. So what is my tangent line at that point? 8x minus 16. Really hold on to please hold on to that idea of how to find the tangent. That's important. Okay. No, there's some really tricky ones. There's some. If I can find it. For the function, find the graph at which the tangent line has a slope of 7. Yeah, that's tricky. Let's do that. Okay, for the function we're given, we want to find the tangent line has a slope. They're saying m equals 7. So we're kind of doing it kind of in the middle, right? Let's see how we can do this. So we know what y equals. Let's find what dy dx equals. All right, well, 2 times 25 is 50. So I'm guessing that's 50. Pretty sure my arithmetic. Decimals always been. Yes, myself. Okay, so there is our derivative. Now they want to know where where the slope equals 7. So that's like f prime of x equals 7. That's what we want to find. Where is that? Where is that? I'm gonna set this equal to that. So negative 0.5 x plus 3 equals 7. Solve for x. Yes, and that's negative 80. 4 divided by negative 0.05. So we found this occurs at x equals negative 80. That's when that occurs. Okay. That's the x. They want the point at which this occurs. So I need to go all the way back up to here. So f of negative 80. There we have it. So I got negative 400. Okay. Let's see what I just did. Why did I do that? They gave me a function and they said, find where this function has a slope of 7. So I found the derivative first. Second, set it equal to the number. This time it gave me 7. So dy dx equals 7. We solved for the x. Then third, we plugged that x into f of x to find y. That's what we did. I think this is a good enough time for me to take a little bit of a break, come back, go over this, because this brings us to the next part. And the next part is just finding a lot of derivatives of different situations. Okay. This is going to be the product rule. So I'm going to take a quick break and then come back and we're going to talk more about how to find specific derivatives. And that's going to lead us into chain rule and product rule. We've already talked about power rule, and I'm going to have to introduce quotient rule as well. Okay. So I'm going to take a 10-minute break, come back. I do apologize for going so fast. There's a lot of concepts. So